Yes, sorry.
Okay. So let's see. I think I'm going to be, because of this business with the second edition and also some dental appointments, I fell jogging home from the office Wednesday, and all sorts of things happened for that. Doctor's appointments and dental appointments and so forth. I'm going to say some things about the Wilson loop and quark confinement. Let me first see if remind you what we took as the Wilson action. It's n over 2k g0 squared, and then 1 minus 1 over n trace of w, and this is then a quarter Faij squared times the fourth power of the lattice spacing. And here, W, of course, is a path-ordered exponential of an integral of, let us say, a bare coupling constant, AI of x dxi integrated around the loop. Okay, now this has all been essentially classical, and if we do this quantum mechanically, we're going to be adding an extra time ordering. So it's a funny sort of operator in which we time ordered the operators and path ordered the matrices. So it's a schizophrenic mathematical object. Now, let me see what I want to say here. First of all, what is this G0? This G0 is a G0 that's going to depend on the lattice spacing. And what we're going to do is to say that this goes to something. In other words, we're going to do computations. We're going to imagine that we shrink the lattice spacing, and then we want, actually, we sort of canceled out the lattice spacing completely here, but we want, if we had kept the lattice spacing, then we would want to do computations as the lattice spacing went to 0, we want to have physical quantities go to constant values. So the idea is that W of A should go to some constant value W as A goes to 0, and as both A goes to 0 and G of A goes wherever it has to go in order to make this go to W in a steady way. Now, let's go back to the continuum theory for a little bit. The basic idea in gauge theories is that the theory be gauge invariant, and if we quantize the theory, what we normally do is we pick a gauge to quantize the theory, and in electrodynamics, the gauge, so in QED, the gauge that one picks is the radiation gauge, which is del dot A. equals 0, and then various things fall out from that, and in particular, one finds that the time component of the gauge field, and we just have one gauge field in QED, is an integral of the charge density over essentially 4 pi. There may be a factor of 2 that I'm missing, but it's an instantaneous potential which suggests that one has broken Lorentz invariance, but it's actually okay. And so one removes A0 from the theory, and instead what you have are 3 components together with a Coulomb term in the Hamiltonian, which is essentially a rho squared of x, rho of x, rho of y over 4 pi x minus y. Now, in QCD, or in a non-abelian gauge theory, so in the non-abelian case, there are various ways in which one quantizes, and in particular, the analog of the radiation gauge, or the Coulomb gauge, is quite awkward in non-abelian theories. Schwinger worked it out, but on the other hand, Schwinger could work anything out. And everybody else uses an axial gauge. And if you use an axial gauge, what you do is you say that one of the components is just is identically 0, and what one normally does is one says that every, let me put the A down here then, one says that every, for every non-abelian field, the ith component is identically 0 throughout space-time, and that's a consistent gauge choice. Here, A would go from 1 to 8 if you were talking about SU3, or A goes just 1, 2, 3 for SU2. Now, of the axial gauges, the one that has always seemed to me to be the most physical is what's called temporal gauge. And in temporal gauge, what one does is one sets the time components of all of the gauge fields equal to 0 throughout space-time. And in temporal gauge, the consequence of this is that Gauss's law takes a particular form, and in particular, it means that that Gauss's law has to, so it's essentially like this, has to annihilate any physical states. Let me just see what. And so in temporal gauge, what one has is that all the physical states, this by the way is the generator of gauge invariant, of a gauge transformation. In other words, this structure here is the generator of a gauge transformation. So one could call this GA phys equals 0, and e to the I theta of x, GA of x, theta A of x. This would be a gauge transformation. And actually we have an integral here, or a product, d4 of x, so that's sort of an arbitrary gauge transformation. Now, what one would do, though, is...
So GA is the Gauss law term, or it's just the...
GA is the generator of a gauge transformation, so G stands for Gauss and gauge.
Okay. No, so is it both the del dot E and the rho? Or is
del
it
dot E A
is G. So you don't have...
minus rho A is G.
Minus rho A, okay. Sure.
So we're enforcing Gauss's law as a constraint on the physical states. And this is an one thing that appeals to me about this is that it seems to be saying something about confinement, although I've never been quite sure what. But in particular, it says that a state that consisted of just one red quark sitting all by itself would be unphysical because it wouldn't be gauge invariant.
So is the index A physical, has physical meaning or not?
The index A is a gauge index, 1 to 8 for SU3, 1 to 3 for SU2. And so if you had a red quark sitting by itself or a green quark sitting by itself, it would not be gauge invariant. And so that would be unphysical. On the other hand, you could say, well, let's quantize electrodynamics in the temporal gauge. And then we'd say that all the physical states had to be gauge invariant. And then you'd say that, well, one electron by itself was also unphysical. So what that means in the case of electrodynamics is that the electron has to be surrounded by a Coulomb field, which makes the whole thing gauge invariant. And so, although this seems to say something about confinement, it's not obvious what it says about confinement.
Kevin, just quick question. How do I see that I would even get some arbitrary function there in U1 gauge theory?
Give me that again.
It's like let's move to the simplest case, U1.
Yeah.
How do I see that del dot E minus rho gives me some arbitrary function?
You mean gives you it generates a gauge transformation?
Yeah. How do I see that?
All right, that's a great question.
It should just
as I said, I
function,
haven't been to Costco lately, so I don't have any more candy.
Mm-hmm. No worries.
All right, well, let's try to understand that, and it's not impossible by any means. First of all, what are so let's look at QED. What are the commutation relations for QED? Well, if you're in temporal gauge, then let's look at what the Lagrangian looks like. It's basically minus a quarter Fij, and so this is going to be a minus, say, b squared over 2, which is the magnetic part. And then it's going to be plus a half EI squared, summed over the 3 spatial directions. Now, EI, I'm doing this without notes, so I'm going to get signs wrong a little bit. EI is essentially di A0 minus d0 AI. But in temporal gauge, this thing is 0.
Yeah.
So the electric field is plus or minus the time derivative of the gauge field. So the conjugate momentum, pi I, let us just say it's a dot. And let me put the minus sign there just to suppress minus signs. So then we have commutation relations like this. AI of x and t, pi j of y and t are delta ij, delta cubed of x minus y. Okay?
Sure.
All right, now, this thing is a dot in the temporal gauge. So this is AI xt aj dot yt is delta ij, delta cubed x minus y. And that's a very nice commutation relation. It's very much like the commutation relations for just a scalar field. Whereas if you keep the A0 term, then you have something which is a transverse delta function, which gives you the more complicated commutation relations, and it means that the gauge field of electrodynamics is a funny gauge field, namely that it has, even though the spinors or the vectors that multiply the annihilation creation operators are 3 vectors, their dot product, the momentum is 0. Okay, so let's see where we were here. So this is the basic commutation relation, and now we're looking for something that generates a change in A. Well, the thing that generates a change in A is AI dot, right? So, and that is EI, and so, all right, so let's just try to construct this thing. E to the I theta grad dot A. That's what grad dot A dot minus rho. This is what I said was going to be so this is del dot E minus rho. I'm saying that this is the generator of a gauge transformation. Well, you can see that, and let's integrate it. And this being a physics department, we're cool about integrating by parts and dropping surface terms. So let's rewrite this as integral minus I integral A dot grad theta plus rho d cubed x. All right, now we want to see what this does to a to two things. First, to a fermion field, and secondly, to a gauge field. So let's have AI, say, of y and t, and e to the minus I integral A dot grad theta plus rho, and then e to the I integral A dot grad theta plus rho. And let's see what this is. And of course, as usual, this being once again the physics department, we work things out in the case of infinitesimal theta where things are simple. So in the case of infinitesimal theta, what we've got is we're going to get that this is approximately AI of y and t, and then it's going to be plus the commutator of AI of y and t with an integral of I integral a dot dot grad theta d cubed x. And I'm dropping out the rho term because rho commutes with a. And now this with that is a delta function. And so this gives us a I of y and t plus I, well, let's just do this, a y of t, and then it's going to be, well, no, there's no a y, there's, sorry. If I do this in a couple of steps, then this is I integral d cubed x. This with that is a delta function of x minus y, and then we have gradient of theta of x, and so this is equal to then a I. Oh, and it's gradient with a delta ij, and this was theta dj, and so this is ay of t plus I times the ith derivative of theta of y and t. Okay, and we decided to do this at a fixed time, namely the same time as y. It turns out that this quantity here, the Gauss's law thing, is in fact time independent. It commutes with the Hamiltonian, so we don't need to worry about the time. Anyway, so we see that this, in the case of QED, this is the generator of gauge translations for the gauge field. And now we want to see how things go for the for a field psi of x and t. Suppose it's a scalar field. So then what's rho? Well, rho of x and t is psi dagger psi of x and t. And so what we've got then is e to the minus I theta rho, e to the minus I integral theta of x and t rho of x and t d cubed x, and then we would have psi dagger y and t psi, let me leave, all right, psi of y of t e to the I integral theta of x and t rho of x and t d cubed x. Once again, we go to the infinitesimal case, and so we have that this. Oh, I don't want
yeah, should it be
sine.
sine?
I just want sine.
Yeah.
And so it's. So let's see. What are we going to use as the? If we can impose fermionic commutation relations.
Yeah, shouldn't the rho in such a case be psi bar psi? If psi, I guess you're saying
if we're dealing with a Dirac field, it would be psi bar psi. I was thinking in terms of a scalar
just
field.
a scalar field, yeah, sure.
And now I'm a little puzzled in terms of the scalar field, because if we had a scalar field, we would have something like this. We would have d mu phi are 1/2, and we'd have a minus sign here. So pi, and let's put a star there. So pi would be the partial of L with respect to phi, and this would, phi dot, and this would be phi star dot. And so the commutation relations are phi with phi star dot is I delta. And all right, maybe I'll stay with fermions since we know what the fermionic ones are. So let's call this psi bar psi of x and p. Anyway, so this is going to be psi of y and t minus I integral beta of x and t, the commutator of psi bar psi of y. Oh, that is x. Sorry. I'll just leave it as x. And psi of y of t. So that's, and this d cubed x. And so what you have here is let's just, all right, let me write this down. It's psi dagger of x, beta psi of x. Let's write it out. Psi of x, psi of y, we're all at equal times, minus psi of y, psi dagger x, beta psi of x. And the psi's anti-commute, and go, so what we've got is psi dagger of x, psi of y, with a minus sign, beta psi of x. And then over here, we've got them in the right order, minus psi of y, psi dagger of x, beta psi of x. And so this is minus the anti-commutator of psi dagger of x, psi of y, times beta psi of x. This gives you your standard delta function. And so this is equal to minus beta psi of x. And why there's a beta there, I don't know. I didn't expect it to be a beta. But so this thing actually is psi of y of t plus I integral beta x and t oh, I left out a delta of x minus 1. And delta x minus y and d cubed x. And so this is turning into psi of y and t plus I theta, and there's this beta, and I'm a little puzzled as to why there's a beta there, actually. Well, anyway, beta is a pretty harmless operator. And So we can approximate this as e to the I theta beta times psi of y and t. And so this is our canonical gauge transformation, although as I said, I'm a little puzzled as to why there's a beta here. But basically, what one sees is that this is a consistent way of thinking. And so,
No, I was just going to say so I guess, the commutation relations don't, it's between psi dagger and psi, right? The commutation relations are.
Psi dagger and psi is commutation relation. Anti-commutation relation.
Oh yeah, sorry, the anti.
So that's why we have an extra beta.
Yeah. It's just kind of fun, because I mean, I don't know, we were talking before about how psi bar psi is actually a Lorentz invariant quantity.
Yeah.
I mean, I guess this thing's going to be a delta function, so it's kind of manifestly Lorentz invariant, but I don't know. Like, should the commutation relations be Lorentz invariant? Or should equal time commutation and anti-commutation relations be Lorentz invariant? Is that, I mean, I guess so,
I don't know if Lorentz invariant is the right term. They're equal time relations.
Yeah.
So it's.
Yeah.
If you have 2 points at equal time and you make a Lorentz transformation, they're no longer at equal time, right?
Suppose so.
I would think. All right, anyway, let me just get another swig of coffee here. So what we've got is, in temporal gauge, we've got this as a constraint on all the physical states. And so now let's think about quarks on a lattice, or quarks in the continuum, and let's imagine, well, first of all, the vacuum state has to be, like all the physical states, has to be gauge invariant. And the way you make a state gauge invariant is you do essentially a path integral over e to the I integral theta del dot e minus rho d cubed x, and you do a path integral over theta. This is the operator then that makes the thing gauge invariant because you're integrating over all gauge invariants. So let's call this thing, I don't know, PG, say. So all the states, all the physical states have to be invariant under this. And this we want, yeah, that's right. And they're invariant under this because this annihilates all the physical states. Okay, so now we imagine that we have, say, a creation operator for some kind of quark at, say, x and, say, times 0. And then we have another an annihilation operator for a quark at another time. And so this creates a quark, and this creates an anti-quark. And we can, and then we have the vacuum state here. And now, when psi dagger of x and 0 multiplies the vacuum state, this thing is no longer gauge invariant. But if we write e to the I integral, and let's suppose these things are separated in the x-axis, so we're going to integrate dx from, let us say, x1 to x2. So if we get the signs right, this will be a gauge invariant quantity, and we may need a coupling constant in here. So I left out the coupling constant would multiply the charge density, or equivalently would multiply the gauge field. Anyway, so this thing is plausibly a gauge invariant state. And now we can imagine at the other end we have omega at a later time, and we might have these same operators, let us say psi x2t, and we're talking here imaginary time, and then this is it integral, this is ax. So this is the, and in fact I've got things wrong. I want to be annihilating this state. So this would be an x there and a dagger there. And now this state here is plausibly gauge invariant. Okay. All right. Now suppose, and we're working in the temporal gauge. Okay. So what we can do is we can add integrals from, in other words, we've got this integration that's going here from, let us say, x1 to x2, and then up here we're going backwards, so we're going from, say, x2 to x1. But now, in temporal gauge, the time derivative is 0, the time field is 0, so we could add these things also, and it wouldn't make any difference if we added them. And so what we get then is that we've got and in fact, if we want to know what the energy of this thing is, then in between there we put e to the minus beta h. So this would be e to the minus beta h, and we'd want to take a limit in which beta grows large, so we project out all the irrelevant states and look just for the lowest energy state. And so this whole thing then is effectively a path integral e to the minus the Euclidean action, and then what's left, the thing that you're taking the mean value of. So e to the minus, the path integral gives us this, and then we would have various Fermi fields here. So what was it? Psi dagger, psi dagger. But then the thing I want to focus on is these things. And because we're in temporal gauge, we can add the integral in the time direction because that field is 0. So what we have here is an integral of G0, say A mu dx mu, and now we're integrating over gauge fields and the fermionic fields. So that's basically what we're looking at. And we now imagine that we're considering this for the case of heavy quarks. And remember last time, this thing is quadratic in the size. If the quarks are heavy, the integration over the fermions is just some determinant that I'm going to ignore. And what we have left is e to the minus the Euclidean action plus G0 in integral A mu dx mu. So far we've done that in terms of temporal gauge. But on the other hand, once we've added these time integrals, this thing is gauge invariant. dA we have to define so as to be gauge invariant. And then this thing is gauge invariant. This is just the Wilson loop. And so we can compute this in any gauge or do the path integral over all gauges. And then that means then that the key to understanding the energy of a quark-antiquark pair is to say, well, let's find the mean value of a Wilson loop that goes a certain distance in space and a certain distance in time. And we expect then that this is going to be e to the minus the energy. Well, we've got a beta here, so let's throw in a beta. We played about betas today. This is a different beta, of course. So it's e to the minus beta e, and what is this going to be? Well, if, let's suppose that this W turns out to be e to the minus beta times the distance between them, x2 minus x1, times some constant b, say. Well, then you would say that the energy of the quark-antiquark pair, or the mass of quark-antiquark pair, would be proportional to its separation. So this is the area law. The area of the Wilson loop is that we have a Wilson loop that goes like this, and it went from, say, x1 to x2, x2 to x1, and then it went a beta direction this way and that way. The area of the thing is beta x2 minus x1. And so if the Wilson loop decays exponentially as the area of the loop, then you have a sort of non-perturbative, certainly non-perturbative derivation of quark confinement. And so that's been the basic idea behind lattice gauge theory since Wilson first proposed it. I'm not sure. I don't remember what he wrote exactly in his papers, but shortly, within a year or two, Kreutz had suggested using the Monte Carlo method to do these integrals. Wilson suggested the compactification of gauge theory that I showed you guys earlier. And in fact, that Wilson loop thing, where the individual in other words, this W is a product of U1, U2, U3, U4, where each U1, each UI is an element of, let us say, SU3. So these are 3 by 3 matrices, and you multiply the 4 of them together, and I went through this in class, right, last week or the week before. And so, but just to review, if you have U1 on this link, and if you have U3 on that link, and U2 on this link, and U4 on this link, then what you actually do is U1, U2, U3 adjoint, U4 adjoint, because you're going backwards that way. And so Freud suggested how one could actually do these integrals using the Monte Carlo method on the lattice. And when I don't know if it was his first paper, but one of his early papers was, or let us say, the paper by Kreutz that caused people to think that there was some truth in this was a computation that he did on a 10 to the 4th lattice. Now, a 10 to the 4th lattice in those days was a big deal, so he was using basically the best computers available. It was around 1981 or 1980 or 79, something like that. And remember, this is on each link you have a 3 by 3 matrix. So it's not just like integrating a scalar field, it's more complicated. Another aspect of that is that when you integrate over this, if you integrate over the scalar field, you just, you choose your new value just by picking a random number of a certain scale size, and you go equally, your chance of going to of increasing or decreasing are both equal. Here, you have a, you want to make sure that your measure for the group integration is a gauge invariant thing that doesn't introduce any distortion or prejudice. And so what you do is you use what's called a gauge invariant measure. In the case of SU2, this is a very simple formula for that. Namely, you can write an SU2 element, U, as e to the I, I'm using A again, where A is the lattice spacing. So let me say just e to the I theta dot sigma over 2. So this would be or put a minus on there maybe. This would be an arbitrary SU2, element of SU2. Now, the surface of SU2 is the surface of a three-dimensional sphere in Hall space. And so what you're doing is you'd be integrating delta of 1 minus so let's see, I should have brought my notes in with me. It's actually in the group theory chapter. But anyway, it's e to the minus, let me use the thing a squared. And dq. I think that is the measure, or in other words, you don't need the integral sign anymore. So the measure d mu of A is delta of 1 minus A squared.
Is A the lattice
It might be
spacing again?
What?
Is A like the lattice spacing again, or no?
No, it's not. It's the parameters. In fact, it's like these thetas. All right, look, let me, if I'm going to show you this, I might as well do it right. So let me grab my notes.
Didn't expect it. Yeah, I think it should just be each thing.
It's integral of the sphere.
Mm-hmm.
Okay. Here, it turns out that you can write the group element as A0 plus I A dot sigma. This is an element of SU2. So as I said, the group manifold of SU2 is the surface of a 3-sphere in 4 space. And so you need 4 A's. And so what you've got is d mu is actually delta of 1 minus a squared d fourth a. And you can then rewrite that as 1 minus a vector squared to the minus 1/2 d cubed a. So that's the actual measure that one uses for SU2. So
Is this the same thing as a Haar measure, or no?
this is the Haar measure.
This is the Haar measure?
And okay, so let's see what so what Kreutz and others showed was that if they did this for SU2 or SU3, that the mean value of the Wilson loop in these simulations was did fall off as an area with an area law. Now, if there is, however, something else that maybe I should say about this. This was something that a guy named Stump and I wrote in a paper some time ago, actually about the time that Kreutz was writing. Namely, we looked at in the continuum at what an integral of let us say a line integral of let's just go to the Abelian case, what AI dxi was as an integral of, let's put an I there. Well, it turns out that actually is something that has infinite energy. And the reason is that whereas Gauss's law generates a gauge transformations on the fields, the matter fields and the gauge fields, this generates a gauge transformation on the electric field. And you'll say, well, the electric field for the case of U1 is gauge invariant, but in the case of, that's interesting, in the case of, in the non-abelian case, it's not. And so this thing generates an electric field, and the electric field that it generates is well, in order to see what it is, what we do is we rewrite this as AI of x, and then we write this as d cubed x. But now to get down to this, to a line, what we would have is a two-dimensional delta function of 3 vector x minus, or it actually would be a three-dimensional delta function of that minus, say, L of u du. This is the line. And so in other words, the electric field that this is generating is proportional to a two-dimensional delta function. And the energy of a two-dimensional delta function is infinite. And so if you're then taking the mean value in the vacuum of a Wilson loop, what you've got to get is 0, because this thing is generating states of infinite energy, and this is giving you what you're really doing is you're taking this in, e to the minus beta h, basically. And so because this is generating states of infinite energy, this thing is actually 0. It just has occurred to me in the last few minutes while thinking about this that that this argument that this thing is 0 seems to be true well, we proved it in general, but we were really looking at the non-abelian case. In the abelian case, in the abelian case, let's see, what I'm wondering about is whether AI is actually changing EI or not. Well, again, if you look at the commutation relations, you've got to pick a gauge in order to figure out what you're doing. In temporal gauge, this would change EI dot and AI dot, and AI dot is EI, and so this would change E in temporal gauge. So in both the abelian and the non-abelian case, the thing would be effectively 0. Let me switch now to something else about this, about gauge invariance. And this is going to be very nebulous, but you know, let's go from Euclidean space to Minkowski space and think about ordinary Feynman path integrals in Minkowski space. Then the amplitude for some initial state to go to some final state is the sum of these exponentials of the action, or I times the action, for all these various paths. And quantum mechanics gives you classical mechanics because the classical paths are the ones that whose actions change only by second order in the change, and so these phases add up very strongly in the case of the classical path. Now let's think in terms of gauge invariance. So imagine that you've got a way of going from this situation to that situation in a gauge invariant way. Then the theory's gauge invariant, and so you can have many other paths that have the same action because it's gauge invariant, and because the process is gauge invariant. And so gauge invariant processes are kind of like classical processes in that they get an enormous reinforcement because of gauge invariance. Now, on the other hand, if you had a process that wasn't gauge invariant, that say went over here, then that would be enormously disfavored. Now, whether that has anything to do with confinement, I don't know, but it somehow suggests that it might. I mean, because if you just had a lonely red quark that went over here, then that wouldn't be gauge invariant. Whereas if you had a red quark and an anti-red quark that go like that, well then that's a gauge invariant thing. So I don't know if that has anything to do with confinement, but I once thought that this temporal gauge restriction that all the states had to be exactly gauge invariant, that was somehow behind core confinement, but a friend of mine talked me out of it, so I never published. Let's see, I did prepare some things to say about scalar fields. Would you like to hear them now, or do you think we should maybe quit?
Go ahead.
Go ahead. No, I'm sort of running out of blackboard. Well, when we were last talking about scalar fields, what we had was an S0 was minus a half a sum, and it was phi of x plus I hat, meaning, remember that x in my notation, which may be a silly notation, I'm writing it as the lattice spacing times a quartet of integers, and it was that times phi of x plus a half times, curiously, we're in 4 dimensions, of course, so it's 8 plus the dimensionless mass squared times the square of the field. So this is just a scalar field, again, at x. And we can rewrite that as a half phi n, k and m phi m, where n and m represent lattice sites. This, say, this, let's suppose I has the value 2. Then x plus 2 hat would be a I j plus 2 k l, and no, I'm sorry, j plus 1. So that's what this notation means. And this matrix K is a very big matrix. It's n to the 4th by n to the 4th if your lattice is n spaces in each space-time direction. So you've got, so it's n to the 4th by n to the 4th. On the other hand, K is almost diagonal. It's a, I guess it's, I don't know, I don't remember the term, but it's sort of a striped matrix. Because after all, it's diagonal in this term, and in this term it's off by 1. So it's almost diagonal.
Is that Toeplitz?
Huh?
Is that Toeplitz?
Is it a Toeplitz matrix?
Yeah, is that what that means?
I hadn't thought of that. I don't know.
It's sort of just kind of like band diagonal.
Yeah, but the trouble is, if we were in one dimension, it would be a perfect band, you see. But you've got the problem that you've got y and z and t, so I'm not sure quite how it works. This thing, if we write it, it's KSU then is a minus a sum I greater than 0 Kronecker delta of s plus I comma u plus s, I'm sorry, that's delta, Kronecker delta, of s minus I u minus 2 delta su plus mu squared delta su. So the 8 comes back here. And in any event, if you are doing the integral e to the minus s0 d phi, well, it's a Gaussian integral because it's quadratic of the s's. And so we can say that this z0 of beta is then a product over all the sites d phi at each site, and then this is e to the minus a half sum phi s k s s prime phi s prime. And this is then the square root of 2 pi raised to the power n to the 4th over the determinant of this matrix K. And here beta is n times the lattice spacing. And well, we're formally at the end of time, and I think maybe this is a good place to stop.